You ask an LLM to solve a math problem. It makes a calculation error. If you point it out, it fixes it instantly. But if you ask it to check its own work, it confidently doubles down. This isn't just a prompt engineering quirk. It's a systematic failure mode called the self-correction blind spot. And until now, we've only been able to describe it empirically. No one knew exactly why generating a token actively suppresses the model's ability to detect its own error. Today, we're breaking down SPARC, a new spectral algebraic theory that finally gives us a formal mathematical account of this phenomenon. We're going to look at why the blind spot exists, how to mathematically trigger self-correction, why reinforcement learning actually works where supervised fine-tuning fails, and how this theory unifies text, image, and video generation under a single mathematical framework. Let's start with the mechanics. Modern autoregressive models, whether they're generating text or visual tokens, update their hidden states through a residual stream. At each step, the model applies attention and MLP blocks, which we can model as Jacobian matrices acting on that residual state. When you generate a token, you're not just adding information, you're transforming the entire state space. If those transformations amplify errors rather than dampening them, the model gets locked into its own mistakes. Prior work showed this empirically. They found that correction success depends on error depth, that reinforcement learning installs correction capabilities that supervised fine-tuning cannot, and that even a simple token like weight can slash blind spot rates by nearly 90%. But without a formal model, these were just observations. We didn't have a convergence guarantee for RL-based correction, no quantitative threshold for when a correction marker would actually work, and no theory connecting text LLMs to autoregressive visual generation. SPARC closes this gap by defining an error-propagation operator. Think of it as the product of all per-step Jacobians along the generation horizon. This operator maps an initial perturbation, like a small error in the hidden state, to its final magnitude after t steps. The key insight comes from linear algebra. The spectral radius of this operator, which is the magnitude of its largest eigenvalue, dictates everything. If the spectral radius is less than 1, the operator is contractive. Errors decay over time. If it's greater than or equal to 1, errors are amplified or preserved. And here's the formal result. The self-correction blind spot exists if, and only if, that spectral radius is at least 1. When the model generates internally, the error travels along the leading eigenvector of this operator. If the radius is 1 or higher, the perturbation never attenuates. The model's own logit distribution gets shifted in a way that makes the incorrect continuation look just as probable, sometimes more probable than the correct one. The model literally cannot detect the deviation. But when an error is injected externally, it enters as a fixed token condition, processed through a separate forward pass. The model evaluates it against an unperturbed context, bypassing the internal amplification dynamics. That's why external correction works, while internal correction fails. So if the blind spot is baked into the spectral properties, how do we break it? SPARC derives a sharp activation threshold for correction markers. We define correction sensitivity as the relative magnitude of the perturbation a marker introduces into the residual stream at the injection point. The theory proves that self-correction activates if, and only if, this sensitivity exceeds a threshold determined by the spectral radius. Specifically, the marker's sensitivity must be greater than 1 minus the spectral radius, divided by 1 plus the spectral radius. This isn't just a theoretical bound. It's tight. It exactly recovers the 89.3% blind spot reduction, observed when models are prompted with the token weight. The token works because its perturbation magnitude crosses the spectral threshold, forcing the operator into a contractive regime where the model can finally see and revise its own mistakes. Now, here's where it gets really interesting for training. We know from recent work that reinforcement learning installs self-correction capabilities that supervised fine-tuning simply cannot. SPARC explains why. In RL-based verifier-corrector pipelines, you're optimizing two coupled objectives. We can represent their interaction as a coupling matrix. The spectral norm of this matrix measures how strongly the corrector's updates interfere with verifier stability. The theory proves a convergence guarantee. RL training converges at a rate proportional to the squared coupling norm over the square root of the number of episodes, but only if that spectral norm is strictly less than 1. If it's greater than or equal to 1, you hit the refinement instability regime, where self-refinement actually degrades output quality. Supervised fine-tuning fails here because it trains on error-free demonstrations. The gradient for the verifier requires exposure to errors, and the corrector has no error signal to optimize. SFT leaves the coupling matrix undefined, so it never installs the contraction needed for stable self-correction. RL with outcome feedback actively drives the spectral norm below 1, contracting the error dynamics and installing reliable correction. And this isn't just about text. Autoregressive visual generation models, whether they're producing images or video tokens, share the exact same residual stream update structure. SPARC proves that the spectral criterion is modality invariant. The token alphabet changes, but the residual stream Jacobian product governing error propagation does not. The same spectral radius condition predicts blind spot behavior across text LLMs, autoregressive image generators, and video models. This unifies a fragmented literature under a single mathematical framework. You might be wondering, if this theory relies on computing Jacobian products and spectral radii, isn't it computationally prohibitive for large models? Not anymore. The theory leverages Hutchinson power iteration with Jacobian vector products. This gives an unbiased estimator of the spectral radius in linear time relative to the sequence length and hidden dimension, with variance that scales predictably. In practice, using 50 Jacobian vector products per model gets you a spectral estimate within 3% root mean squared error of the exact value. Experiments across 4 backbones, including both SFT and RL-trained text models and a visual autoregressive probe, validate every theorem. The spectral predictions match measured blind spot rates with 3% RMSE. Ablations confirm that removing the adaptive threshold degrades performance, removing the coupling constraint destabilizes RL training, and restricting the theory to text-only sacrifices cross-modal gains. The math holds up under empirical pressure. So what does SPARC actually give us? It turns a collection of frustrating empirical phenomena into consequences of a single spectral invariant. The blind spot isn't a bug in the prompting, it's a property of error amplification in the residual stream. The weight token works because it crosses a mathematically precise activation threshold. RL beats SFT because it contracts the verifier corrector coupling below the stability boundary. And this behavior is fundamentally tied to the architecture's residual stream dynamics, not the modality. For researchers building reliable reasoning systems, this means we finally have a predictively checkable criterion for self-correction capability. We can estimate the spectral radius, design markers or training objectives that respect the activation threshold, and monitor coupling norms to prevent refinement instability. The blind spot is no longer a black box. It's a solvable spectral condition. If you want to dive into the proofs, the Hutchinson estimator implementation, or the full experimental ablations, the paper breaks down exactly how to compute and apply these criteria in production-scale models. Understanding the spectral geometry of autoregressive generation is the next step toward building systems that can actually trust their own reasoning.